So this video is on different ways of writing electron configurations, which have different uses. Okay, for we've done electron configurations that are regular. That's like, for example, oxygen has 8 electrons. Its regular configurations: 1s2, 2s2, 2p4, because it has 8 electrons. All right, so I didn't want to redo that one, but that's its electron configuration. Its shell notation, which you can find on your Regents reference table, is just 2, because it's got 2 electrons in the first energy level, and then 6. It's got 6 electrons in the second energy level. So that's a shell notation. The noble gas configuration is a shorthand. Okay. Now remember, the noble gases are the last column in the periodic table. Okay. So if you look where oxygen is, oxygen, like here's your periodic table, right? You got oxygen here, right? And this helium here, and oxygen's like over here, right? You follow? Helium's electron configuration is 1s2. So what they basically do is you go back from whatever element you're doing to the first noble gas, which is going to be in the previous row, right? So for oxygen, its noble gas configuration is going to contain helium. Now, what they're basically showing you is the core electrons. These are electrons that are not going to be involved in bonding. So, and sometimes it's an easy shortcut because the electron configuration is really large, and you don't want to bother, right, with writing out a huge electron configuration when you really only care about the electrons in the outer shell, which are going to be involved in bonding. So the noble gas configuration for oxygen would just be this. It'd be, you put He like that. Now that covers the 1s2, followed by all the electrons after helium. And that's important because these are the electrons that might be involved in being lost, gained, or shared in a chemical reaction. These electrons here are the core, so we kind of ignore them. Now, orbital notation, okay, is showing you the orbitals in which the electrons are located. So for oxygen, right, oxygen's electron configuration gives 1s2, 2s2, 2p4. Now, I'm going to draw a box for an orbital. This is the 1s orbital. This is the 2s orbital. And the 2p sublevel has 1, 2, 3 orbitals. And I'm going to fill these in very carefully, okay? So this is your 1s orbital. This is your 2s sublevel with 1 orbital. And this is your 2p sublevel, which has 3 orbitals. And I'm going to draw the electrons in there. Now, the way I draw them is I try to illustrate a concept called opposite spin. If 2 electrons in the same orbital will have opposite spins. So I'll draw 1 electron with an up arrow and 1 with a down arrow. That represents 2 electrons in the 1s orbital. I will do the same thing for this one. 1 here, 1 here. Now, for the 2p sublevel, I have to be very careful because electrons will not double up in an orbital if there's another orbital that's empty of equal energy. And all the orbitals within the sublevel are of equivalent energy, right? So watch how I do this. I put the first one here, the second one here, the third one here, and the fourth one here. I only double them up when there's none remaining. In other words, let me show you what I would not do, right? What I would not do is this. I'm going to draw again, box, 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 right? I would not do this, 1, 2, 1, 2. Electrons are not going to double up in orbitals if there's another orbital of equal energy that's empty. So the way that would work out would, I'd have to double up one of the orbitals because I got 4 electrons and 3 orbitals, but I'm not going to double up 2 electrons if I don't have to. So I'd have 2 electrons in single orbitals and one of them in the 2p sublevel. And if I were to describe this orbital notation, I would say, it has 5 occupied orbitals, 3 occupied sublevels, 2 completely filled sublevels, 1 partially filled sublevel, and it has 2 partially filled orbitals and 3 completely filled orbitals. These 2 orbitals are partially filled. All right, and that will affect how atoms react and bond. So it's actually an important thing, even though it seems like you're just counting beans, as it were. Okay, let's try another one on the next page. Okay, so let's do one that's a little bit more difficult. Okay, let's do vanadium again. Vanadium is not huge, but it's it's a little more. Now vanadium has, I think, let's see, 18, 19, 20. It's got 23 electrons, right? I like it. It's the Swedish goddess of beauty. That's what it's named after. Very pretty element. Here we go. Anyway, the electron configuration, the regular one is 1s2, 2s2, 2p6, 3s2, 3p6. Again, we go to the 4s first, and then we have the 3d3. Okay? Now that is our regular configuration. Our shell is going to be just 2-8-8, I'm sorry, I messed that up. Erase. 2-8, and the third energy level has 2 plus 6 plus 3 has 13 electrons, and the fourth one just has 2. So that's your shell configuration, right? All right, this is now noble gas. Okay, vanadium is located right here. The noble gas closest to it, before it, has to be before it, is this guy over here, argon. Now, argon ends in 3p6, right there. This will be the, I'm just boxing, this will be the electron configuration for argon. So the noble gas configuration of vanadium would be bracket Ar, and then I wouldn't have to write this whole thing out. Just write out the stuff that happens after argon. 4s2, 3d3. Now, a lot of times when I do an orbital notation, I'm not going to make you write out all the orbitals because all the orbitals up to argon are going to be completely filled by definition. You're not going to start the 4s until you finish the 3p. So if I want to write the orbital notation, I might just write out the orbital notation for the 4s and for the 3d. Now, for the 4s, I'm going to draw one box again, up, down. For the 3d, 1, 2, 3, 4, 5 boxes, because there's 5 orbitals, but I've only got 3 electrons, so they're going to go 1, 1, 1. Notice I didn't double any up. I wouldn't do that, right? All right. Now, what if I did this element over here, which I don't even know which one it is? Okay, I can look it up. I guess I'll look it up. I think that's nickel. Am I at nickel? Yeah, it's nickel, Ni. That's got 28 electrons. Nickel is going to be, you know, well, I'm not going to do the whole thing. Let's just do the noble gas for nickel, right? Nickel's is here. Its previous noble gas is still going to be argon. It's still going to be Ar. Kind of speeds you up too, right? And it's going to be 4s2, but this time it's going to be 3d 1, 2, 3, 4, 5, 6, 7, 8. 3d8. All right? Okay, that is the noble gas configuration. What about the orbital notation? Well, for just the outer electrons, I would do the 4s, and I would do the 3d. And again, I'm going to draw one box for the 4s, and 1, 2, 3, 4, 5 for the 3d. I'm 1, 1, 1, 1, 1. I got 3 left, right? 1, 2, 3. This is filled, obviously, as well. Okay? And so for nickel, there would be 2 half-filled orbitals in the electron configuration. Remember, if you didn't follow the rule here, you would have doubled up this one, so you would have 1 empty orbital and 4 completely filled orbitals in the d sublevel, which would be an incorrect answer.